When you imagine alien life, what comes to mind? Towering creatures with massive brains, advanced starships crossing galaxies, or perhaps tentacled beings manipulating technology beyond our comprehension. Here's the truth that might shatter those Hollywood dreams. If alien life exists out there, it's probably invisible to the naked eye, simpler than a blade of grass, and utterly uninterested in building space empires. The universe is teeming with life, but not the kind that sends radio signals or builds monuments. Instead, it's crawling with microscopic survivors that make Earth's toughest extremophiles look like delicate flowers. These alien microbes are the true masters of the cosmos, and understanding why requires us to dive into one of the most humbling realizations in all of astrobiology. Every second that passes, somewhere in the universe, a microorganism is solving problems that would instantly kill any complex life form. While we struggle to survive a few degrees above or below our comfort zone, these microscopic aliens are thriving in boiling acid, frozen wastelands, and radiation fields that would cook us in seconds. They represent the most probable face of extraterrestrial life, and the mathematics behind this conclusion is as beautiful as it is sobering. Think about this for a moment. On Earth, single-celled life dominated for over 2 billion years before anything remotely complex appeared. 2 billion years! That's almost half the age of our planet spent perfecting the art of being simple, tough, and nearly indestructible. Complex life, the kind that builds tools and contemplates the stars, has existed for a cosmic blink of an eye in comparison. The evolutionary journey from microbe to civilization is like climbing a mountain where each step becomes exponentially more difficult. First, you need the basic chemistry of life to emerge from non-living matter. Then those early cells must survive long enough to reproduce and evolve. Next comes the monumental challenge of developing more complex internal structures like nuclei and specialized organelles. After that, multiple cells must learn to work together, abandoning their independence for the greater good of multicellularity. Each of these transitions represents a bottleneck so narrow that most worlds probably never make it through. The mathematics are staggering. While microbes need relatively little energy and can adapt to almost any environment, complex organisms demand perfect conditions, abundant resources, and stable climates for millions of generations. Consider the energy requirements alone. Recent studies show that multicellular organisms need more than 10 times the energy of their single-celled cousins just to maintain their basic functions. That's not including the energy needed for complex behaviors, large brains, or technological development. In a universe where most planets exist in extreme environments, this energy penalty becomes a death sentence for anything more complex than a bacterium. But let's get specific about what these alien microbes might actually look like and where they're hiding. The most exciting targets aren't the Earth-like worlds of science fiction, but the hellish environments that would instantly destroy any complex life form. Take Europa, Jupiter's ice-covered moon. Beneath its frozen surface lies an ocean containing twice as much water as all of Earth's seas combined. This ocean exists in perpetual darkness, under crushing pressure, bombarded by radiation that would be lethal to any complex organism. Yet this nightmare environment could be paradise for microbial life. The seafloor might host hydrothermal vents spewing chemical energy, while the ice above protects against the worst radiation. Any life here would be simple, hardy, and completely alien to our surface-dwelling perspective. Mars presents another compelling case. Its surface is a frozen desert, bombarded by radiation and soaked in toxic chemicals called perchlorates. The atmospheric pressure is so low that liquid water instantly boils away. These conditions would kill any complex life form in minutes, but several meters below the surface, conditions become more hospitable. Protected from radiation and temperature extremes, microbial communities could potentially thrive in underground brines, extracting energy from chemical reactions between rocks and water. The truly remarkable thing about these potential alien microbes is their incredible diversity of survival strategies. On Earth, we've discovered bacteria that eat radiation for lunch, organisms that thrive in acid so strong it would dissolve metal, and microbes that remain dormant for millions of years before springing back to life when conditions improve. If Earth's microbes can do this, imagine what alien evolution might have produced in environments even more extreme than anything on our planet. These extraterrestrial microorganisms would likely be masters of chemosynthesis, deriving energy from chemical reactions rather than sunlight. They might form vast underground networks, cycling nutrients and energy through planetary systems we can barely imagine. Some could be living fossils, preserving ancient biochemistries from their planet's early history. Others might represent evolutionary experiments that never occurred on Earth, using completely different molecular machinery to sustain life. The search for these microscopic aliens has already begun in earnest. Future missions to Europa and Enceladus will drill through ice to sample subsurface oceans. Mars rovers are digging deeper into the red planet's subsurface, hunting for signs of past or present microbial activity. The James Webb Space Telescope is analyzing the atmospheres of distant worlds, looking for chemical signatures that could only be produced by living organisms. What makes this search so compelling is that finding even a single alien microbe would revolutionize our understanding of life itself. It would prove that biology is not a unique accident that happened once on Earth, but a fundamental feature of the universe. Every drop of water, every chemical gradient, every energy source becomes a potential habitat for life when you realize how incredibly adaptable and resourceful these microscopic organisms can be. The implications extend far beyond simple discovery. These alien microbes could hold the keys to understanding how life begins, how it adapts to extreme conditions, and perhaps even how it might be cultivated in space. The sheer abundance of potential microbial habitats across the galaxy becomes staggering when you start mapping them out. Every icy moon, every subsurface ocean, every hydrothermal system represents billions of potential homes for these microscopic colonizers. While complex civilizations need perfectly balanced planets with stable climates, protective atmospheres, and abundant liquid water on their surfaces, microbes can make themselves at home in places that would seem like pure science fiction nightmares. Picture the volcanic moon, Io, constantly reshaped by tidal forces that generate incredible heat and sulfur compounds. The surface is a hellscape of active volcanoes and toxic gases. Yet beneath this chaos, chemical energy flows like rivers. Microbes that evolved to harvest sulfur compounds could build entire ecosystems in environments that would vaporize any complex organism in seconds. These aren't just theoretical possibilities. They're the most probable scenarios based on everything we know about life's incredible persistence. The timeline argument becomes even more compelling when you consider the vast scales involved. Complex civilizations, if they exist at all, represent tiny flickers in cosmic time. Even if an advanced species somehow overcame all the evolutionary hurdles to develop technology, they face existential threats that microbes simply laugh at. Solar flares, asteroid impacts, climate catastrophes, resource depletion, wars, plagues, the eventual death of their star. Any of these events could erase millions of years of evolutionary progress in an instant. Microbes, meanwhile, are virtually indestructible. They've survived every mass extinction event in Earth's history. When the asteroid that killed the dinosaurs turned our planet into a molten wasteland, microbial communities just went dormant and waited it out. Some species can survive direct exposure to the vacuum of space for years. Others can withstand radiation doses thousands of times higher than what would kill a human. They represent life stripped down to its most essential, unbreakable core. This creates a fascinating paradox in our search for extraterrestrial intelligence. The more we learn about the requirements for complex life, the more we realize how incredibly rare it must be. Yet the more we discover about microbial extremophiles, the more we understand that simple life is probably everywhere. The universe isn't empty and lifeless. It's absolutely crawling with microscopic aliens that we're only just beginning to detect. Recent discoveries have shattered our assumptions about where life can exist. Scientists have found thriving bacterial communities in clouds, in solid rock miles beneath the Earth's surface, in the most acidic hot springs, and in frozen Antarctic valleys that haven't seen liquid water for millions of years. Each new discovery expands the map of potential alien habitats and reinforces the same conclusion. If you're looking for aliens, think small. The technology we're developing to find these microbial aliens is becoming incredibly sophisticated. New instruments can detect the chemical signatures of life in samples smaller than a grain of sand. We're learning to recognize the subtle patterns that living processes leave behind, even after millions of years. These biosignatures could be preserved in Martian rocks, floating in the geysers of Enceladus, or drifting through the atmospheres of distant exoplanets. But perhaps the most profound implication of ubiquitous microbial life is what it means for our own place in the cosmos. We've spent centuries assuming that intelligence and technology represent the pinnacle of evolution, the inevitable destination that life strives toward. The reality appears to be exactly the opposite. Intelligence might be an evolutionary accident, a bizarre experiment that occasionally emerges, but rarely survives long enough to matter on cosmic scales. The microbes, meanwhile, are the true success story. They've conquered every environment, survived every catastrophe, and will likely outlast every complex species that evolution produces. They are the universe's chosen ones, not because they're the most advanced, but because they're the most adaptable. When our sun finally dies and Earth becomes uninhabitable, the last survivors won't be humans or any other complex species. They'll be the descendants of microorganisms that have been perfecting the art of survival for billions of years. This perspective completely transforms how we think about astrobiology and our search for extraterrestrial life. Instead of scanning the skies for radio signals from alien civilizations, we should be preparing for a universe where life is common, but consciousness is vanishingly rare. Instead of expecting to find alien cities, we should be getting excited about discovering alien chemistry hidden in subsurface oceans and underground rivers. The beauty of this realization is that it makes the search for life both more realistic and more immediate. We don't need to wait for signals from distant star systems or develop interstellar travel to make contact with alien life. The aliens are probably right here in our solar system, waiting to be discovered in places we're already planning to visit. The next time you gaze up at the night sky and wonder if we're alone, remember this: we're almost certainly not. The universe is alive, thriving, and absolutely teeming with microscopic aliens that are right now solving impossible problems in impossible places. They may not build starships or send us messages, but they represent something far more profound: the unstoppable persistence of life itself. The cosmos belongs to the microbes, and honestly, that's probably exactly as it should be.